Hello, students. Welcome to the 10th lecture on particle physics. And today we are going to discuss about quarks, why they were proposed. As we know that they were proposed first theoretically, and then after many years they were experimentally found through indirect methods like the experiment similar to what we had almost 60 years ago for the Rutherford alpha scattering experiments. Now, what we have discussed in the class that nucleon resonances have been observed, and we have the delta resonance, N star resonance, 1535, 1650, 1720, etc., and many more. And these resonances have different spin, these resonances have different parity, and similarly, if we look at the particle data booklet, we'll find that really the second column represents the spin of the particles with parity, the third column represents mass, and the fourth column represents the status of the observation of these particles. 4 star represents that they have been confirmed, and single star means they need more evidences. Therefore, as you can see that there are many nucleon resonances. If you look at the spectrum more carefully, then what you will realize that we have nucleon resonances, that means all those particles with a spin half in the different states, resonant states, and similarly we have starting from delta, which is a spin 3 half particle, then we have higher resonances, those exist here also. Therefore, the resonances were compelling us to think that these nucleons are not fundamental objects, as they can be excited to some other state, unlike electron, where if we impart energy to the electron, all the energy is taken by the electron as the kinetic energy. Not only this was observed for the nucleons, but even for the mesons also, as you can see that the x-axis corresponds to the center of mass energy and the y-axis cross section. As you can see at the resonances, we have these peaks. Therefore, these peaks corresponds to the observation of many resonant states. Therefore, we had the baryon resonances as well as we had the meson resonances, and there are again, like in the case of baryons, here also we have scores of mesons which have been observed in nature in the different experiments. Therefore, as you can see, we have not only pions, kaons with pions 140 MeV mass. As you can see, these are the particles with different spin, with different parity, etc., etc. Therefore, these resonant states were compelling us that these hadrons are not fundamental objects. Similarly, the other point which we have discussed in the class, that if we assumed that the magnetic moment of proton should be the same as the magnetic moment of the electron, as given by the for the electron Eh cross upon twice Me, this is known as one Bohr magneton. For the proton, it should be Eh cross upon twice Mp, and since mass of the proton is 1836 times more than the mass of the electron, therefore, since it is coming in the denominator, it's expected that mass of the magnetic moment of the proton will be 1836 times smaller than the magnetic moment of the electron. And this is known as one nuclear magneton. But what has been experimentally observed, that it is not one nuclear magneton, rather it is 2.79 nuclear magneton. And this 1.79 is known as the anomalous magnetic moment. Similarly, for the neutron, which has got zero charge, the magnetic moment should be, by this definition, should be equal to 0, while it has been observed that the magnetic moment of the neutron is minus 1.2 91 nuclear magneton. And similarly, that is true for other baryons. Those have been listed here, or the antiparticles which have been listed here. The magnetic moment has been found out to be different from normal. Anomalous is different from normal. Therefore, we had this part 1.79. It is extra. Then from the definition, if like electron, which is a point particle, which is a structureless particle, its magnetic moment is just one Bohr magneton, while here the magnetic moment is quite different. And therefore, these resonances and magnetic moments were compelling us to think some out of box idea. And the Mendeleev of elementary particle physics was Murray Gell-Mann, though this was also proposed simultaneously almost by Neumann, who in 1961 introduced the so-called eightfold way. And this eightfold way arranged the baryons and mesons into some weird geometrical patterns according to their charge and strangeness. For example, if we talk about all low-lying baryons having a spin half and parity positive, those were known at that time: proton, neutron, lambda, sigma plus, sigma 0, sigma minus, cascade 0, and cascade minus. They arranged these 8 particles into a geometrical pattern, something like this, where proton, neutron, they were sitting at the top, then sigma plus, sigma 0, lambda 0, sigma minus at the center, and then cascade 0 and cascade minus at the bottom. And what was the important point? The important point was the particles which are lying on the same line, if you switch off the electromagnetic interaction, then they have got the same mass. Therefore, all those 4 particles, when you switch off the electromagnetic interaction, the masses are the same. Similarly, that is true for proton and neutron and cascade 0 and cascade minus. Then the charges of these particles, as you can see this line, diagonal line, all those particles which have charge plus 1, they lie on this diagonal line. All those particles which have charge 0, they lie on this diagonal line. And all the particles which have charge minus 1, they lie on this diagonal line. Then the strangeness of all the particles lying on the first line, this is 0. For the second, strangeness is minus 1. And for the third, strangeness is minus 2. Moreover, the mass difference between these two, the top line and the central line, for all the particles, that is the same as the mass difference between the central line and the bottom line. Therefore, the mass difference is, say, if I am representing it by delta m, then that delta m also exists for the mass difference between the particles, say cascade 0 and sigma 0. Therefore, the mass difference between sigma 0 and n was found out to be almost the same as the mass difference between cascade 0 and sigma 0. Therefore, they found that the particles which have got a spin half parity positive, they can be arranged in this geometrical pattern. Not only this was true for the low-lying baryons, but this was also found to be true for the mesons known at that time. The mesons were pi plus, pi 0, pi minus, k plus, k 0, k 0 bar and k minus, and eta 0. These were the 8 particles known at that time. All these particles have spin 0 and all these particles have got parity odd. Similarly, what was found that this particle has got straightness plus 1, this particle has got straightness 0, this is minus 1, this is also a straightness 0 particle. Therefore, they placed pi plus, pi 0, eta 0 like this. Pi plus, pi 0, eta 0, pi minus, k plus, k0, k0 bar, and k minus. All those particles lying here have straightness plus 1, here straightness 0, and here straightness minus 1. Again, the diagonal line, all the particles have charge plus 1. Here the particles have charge 0, and here the particles have charge minus 1. And also the mass difference here is almost the same as the mass difference here. Therefore, they found out that really these particles can be fitted in these weird geometrical patterns. As we have seen that 8 lightest baryons with the same spin half fit into a hexagonal array with two particles lying at the center, sigma 0 and lambda 0, and he called this group of particles as the members of baryon octet, 8 particles. Particles of like charges lie on the downward sloping diagonal lines, and horizontal line associate particles of the same straightness quantum number. As you can see here, this is the picture. All the particles which have been shown here, their baryon number is plus 1 and their spin is half, parity is positive. As you can see, here we have straightness 0 particle, here is straightness minus 1 particle, here is straightness minus 2 particle. This mass difference is the same as this mass difference, and the charges, as you can see, is plus 1 here, 0 here, and minus 1 here. You can see that straightness is 0, minus 1, minus 2. Then charges on these diagonal lines plus 1, 0, and minus 1. And the mass differences are also almost the same between these two. Similarly, 8 lightest mesons with the same spin, that is spin 0, with parity out, fill a similar hexagonal pattern, forming the meson octet, 8 particles, which we have discussed earlier. And here also horizontal lines associate particles of the same strangeness quantum number, and the charges lie along the downward sloping diagonal lines. This time the top line has straightness plus 1, as we have shown, k plus and k0, and the central line has straightness 0 particle, pi plus, pi 0, eta 0, and pi minus. And then we have straightness minus 1 particle as k0 bar and k minus. In the case of the mesons, the antiparticles lie in the diametrically opposite positions in the same supermultiplet as corresponding to the particles, as we had pi plus here, pi minus here. Okay, and similar hexagon you can plot for all those mesons which have spin 1, like rho plus, rho 0, and rho minus, omega 0, k plus star, k0 star, k0 bar star, and k minus star. These are the particles. Therefore, the other sets that you can form, rho plus, rho 0, rho minus, here k plus star, k0 star, k0 bar star, k minus star, and here we have omega 0. Again, an octet of 8 particles. We have to remember that k plus is entirely a different world from k plus star, because k plus is a spin 0 particle, while k plus star is a spin 1 particle. Therefore, k plus has nothing to do with k plus star. We should not get confused by the name. Similarly, we have here rho plus, sorry, I should plot rho plus here, like pi plus we had done. Therefore, rho plus, rho 0, omega 0, rho minus, these are all vector mesons. These are spin 1 odd parity particles. These are called vector mesons. While with the earlier case, we had pseudo scalar mesons. Therefore, you can see that here I have shown the pseudo-scalar mesons because they have got spin 0 and parity positive. If this spin is 0 and parity is positive, then we call it as scalar meson. While if spin is 0 and parity is odd, we call it by the name pseudo-scalar meson. Pseudo-scalar meson. Similarly, we have vector meson, and then we have spin 1 but parity positive. These are known as pseudo-vector meson. This is vector meson. Therefore, this is pseudo-vector meson. Therefore, as you can see, there are 8 particles. Top one has a straightness plus 1, the middle one has a straightness 0, and the bottom one has a straightness minus 1. Then the diagonal lines, extreme right dashed line is charge plus 1, central charge 0, and extreme left charge minus 1. Therefore, from right to left, you see it is in decreasing order of the charge. From top to bottom, it is in the decreasing order of strangeness. And what I am telling you, that mass difference here is the same as the mass difference here. That is what I am showing it by putting delta M. Now, this eightfold way not only had hexagonal patterns, but an inverted triangular array incorporating baryons with J is equal to 3/2. Therefore, not only they plotted lowest lying baryons with a spin 1/2 and the lowest lying mesons with a spin 0, but they also had delta plus plus, delta plus, delta 0 and delta minus, sigma plus star, sigma 0 star, sigma minus star, cascade 0 star, and cascade minus star. And here the 10th particle was missing at that time. Therefore, not only they had the hexagonal array, but they had an inverted triangle where Gell-Mann accommodated 10 particles and called that as decuplet of particles. And the 10th particle was missing at that time. He boldly predicted that particle. Not only he predicted that there should be a particle, but also he predicted its spin, its charge, its lifetime, its mass. And that was the great success of this eightfold way pattern. As you can see that all the particles lying at this vertex has charge plus 2, this vertex charge plus 1, this vertex charge 0. Therefore, he predicted that this unknown particle should have charge minus 1. Then delta, we know that delta's mass is 1232 MeV. Therefore, this mass is around 1380 MeV. This mass is around 1530 MeV. Therefore, there is a mass difference of 150 MeV here, 150 MeV here. Therefore, he predicted that there should be a particle with a mass of 1680 MeV with a difference of 150 MeV. Therefore, he predicted the mass of this particle to be 1680 MeV, spin of this particle to be 3/2, parity of this particle to be positive, and moreover, besides this, he also predicted the lifetime of this particle. Therefore, the important great success of this eightfold way was the prediction of this 10th particle, which was later observed in the experiments at BNL. And this particle was observed in 1964. And not only that, in the 60s, we had, with the development of accelerators, we observed many new hadrons, and they found a place in one of the eightfold way supermultiplets. Similar to the particle octets and decuplets, there exist anti-baryon octet, anti-baryon decuplet, because we are talking about proton, neutron, lambda, sigma. They are all particles. They have all got baryon number +1. But what happened that we had anti-proton, anti-lambda, anti-sigma, etc. particles. Therefore, we had a similar octet for anti-particles, and therefore these weird patterns were also found to be there in the case of anti-particles. Therefore, here I am showing the decuplet. As you can see, starting the 4 deltas at the top, then 3 deltas on the second line. In the third line, we have 2 cascade stars, and the final one, the 10th one, was not there. Therefore, I have put a sign of integration. And what has been observed, that this charge of this particle is +2, and this particle, the fourth line in this, on this line, that charge is -1. And the mass difference here, 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 and here, 150 MeV each. Therefore, he predicted that this particle should have a mass of around 1680 MeV. And this was observed at Brookhaven National Laboratory in the experiment of K minus scattering on the proton target, where we had omega minus, K0 and K plus in the final state. Therefore, the steadiness of this particle was also predicted as -3, and the charge of the particle, the mass of the particle, the lifetime of the particle, etc. were predicted based on the eightfold way. Now, this particle, that is why I have put it here, is nothing but omega minus. The question arises, why do the hadrons fit into these bizarre patterns? In 1964, much before the experiment similar to Rutherford alpha particle experiment, Gell-Mann and Zwick independently proposed that all hadrons are in fact composed of even more elementary constituents. And let me tell you what was the driving force behind that. The excitation of nucleons, the observation of nucleon resonances, the observation of anomalous magnetic moment of the hadrons, and then falling those hadrons into the different weird geometrical patterns. That motivated Gell-Mann and Zwick to think about some fundamental structure inside the hadron. Gell-Mann chose the word quarks from the James Joyce novel Finnegan's Wake, where the line is 3 quarks for master mark, while Zwick called it asses after the 4 asses in the playing cards, because they speculated there were 4 of them on the basis of the 4 leptons known at that time, nu e, e minus, and nu mu, mu minus. Therefore, Zwick predicted 4 quarks, while Gell-Mann said that there should be 3 flavors of quarks, namely up, down, and strange, and they form a triangular eightfold way pattern. This is the pattern which I am showing it. The left hand side is for the quarks and right hand side is for the anti-quarks. What it was argued that the baryons are made up of 3 quarks and mesons are made up of a quark anti-quark pair. And all these quarks have baryon number 1 by 3 plus 1 by 3, and anti-quarks baryon number as -1 by 3. Then U quark has the charge +2 by 3 in units of electronic charge, and D and S have charges -1 by 3 in units of electronic charge. And the argument was that these 3 quarks, they make a baryon, and 3 anti-quarks make an anti-baryon, and quark anti-quark pair make a meson. And with this, we will come to this diagram again by when we will talk about why they opted for y on the hypercharge on the y-axis and I3 on the x-axis. But today, for the completeness sake, just try to understand that this left hand side is for the quarks. This is the three particles SU3 or the SU3 multiplets, and then we have three antiparticles, and U and D quarks were kept in a doublet while S was kept in a singlet. Therefore, for the doublet, U had the highest charge. Therefore, U had I3 plus half and D had I3 minus half, while this was for U, this was for D, while strange quark was a singlet. Therefore, this I3 was 0 for the strange quark. And using this, what they did, they found out, and we will do it in one of the classes, that if we repeat this operation for 3 cross 3 cross 3, then we will get a decuplets and 2 octets and 1 singlet. And we will see that how the decuplet which I have shown for the deltas, and then here for the proton, neutron, etc., we can generate with this concept of 3 quarks inside the baryons and quark anti-quark pair inside the meson. And most important point, that when they were developing this, what was interesting, that initially they had 8 particles, but here 3 cross 3 bar was giving us 8 plus 1 singlet, and they predicted that actually we are missing a particle. They call it by the name eta 0 prime. They predicted its spin, its mass, and all that properties associated with this particle. And they said that actually in the case of meson, the pattern is not octet, but it is a nonet, and therefore we have meson nonets, 9 particles, while we have baryon decuplet, baryon octet, etc. Therefore, this is how they predicted that eta 0 prime, shown here, that eta 0 prime should be there, and they predicted the strangeness, charge, mass, spin of this particle, which was later observed in the experiment. Therefore, using this eightfold way, many particles were predicted, and later they were seen. For example, here I am showing it. This was the lowest lying meson resonance. Then at the like in spectroscopy, we have the different higher lying multiplets. For example, here I am showing 9 mesons which had in the state 3p0. Similarly, another 9 mesons in the state 3p1, another 9 mesons in the state 3p2, and all these mesons which I am listing here, they have been experimentally observed, and these particles have different masses. Therefore, and they are not the same as what we had initially for the ground state meson with spin 0 and parity odd, or a vector meson with spin 1 and parity odd. These are all the different higher multiplets which were predicted in the eightfold way in the different higher states. Similarly, we have in another higher multiplet a set of 9 mesons. Therefore, this was the beauty of eightfold way, that people were able to predict many unknown particles which were experimentally then observed. To summarize, the study of mesons and baryons revealed patterns that could not be explained solely by the known particles with protons, neutrons, and pions. These inconsistencies led to the proposal of quarks as subatomic constituents, each carrying fractional charge. There are 6 types of quarks that we will learn: up, down, strange, top, and bottom, combined to form various baryons and mesons with distinct properties. And the anomalous magnetic moment of the hadrons was really a driving force to think of the idea that there should be some fundamental object inside these hadrons. Therefore, the postulation of quarks offered a solution, explaining these anomalies by considering the intrinsic magnetic moments of quarks within hadrons. Then we should also notice that when we are talking about these octets, we had proton, neutron here, sigma plus, cascade 0, etc. here, sigma minus, sigma 0, lambda 0, and cascade minus. The masses of these particles are different from the masses of these particles, and they are different from the masses of these particles. While proton and neutron, when we switch off the electromagnetic interaction, they have got the same mass. Similarly, that is true for sigma plus, sigma 0, and sigma minus. Therefore, all these particles, they are which are initially which we put them in a doublet or triplet, or for cascade 0 and cascade minus in another doublet. These have the same masses, but for the others the masses are different. In 1950, it was tempting to regard these 8 baryons as a super multiplet, and they belong to the same representation of some enlarged symmetric group in which SU2 of isospin could be incorporated as a subgroup. The question is, what is that larger group? Gell-Mann argued that larger symmetric group is SU3, and the octet constitute 8-dimensional representation of SU3. The decuplet is a 10-dimensional representation, etc. But again, let me point out that proton, neutron, K plus K0, K minus K0 bar, etc., they form a fundamental representation of SU2. But this is not true in the case of SU3, where we are finding out that mass of cascade is much different from mass of sigma, and that is different from proton and neutron. So this rule was preserved for quarks, U, D, and S, which form a 3-dimensional representation of SU3. Now, the other important point was that with the necessity of charm quark to understand the branching ratio of KL0 to be just 10 to the power minus 8, smaller than 10 power minus 8. That means KL0 was not found out to decay into mu plus mu minus, while K plus was found out to decay into mu plus and nu mu. This branching ratio was less than 10 power minus 8, while KL0 is made up of ds bar quark. This is made up of us bar quark. Therefore, what was found out that this is not possible. And to explain this, to understand this, that the branching ratio is small, it was proposed that actually we don't have only 3 quarks. We need one more quark, that was the charm quark. That we need charm quark, and with the help of charm quark, we can understand these processes which have not been observed, that the flavor changing neutral current here, they are changing flavors, but there is no change in the charge. Therefore, the net charge is 0. D charge is minus 1 by 3, and S bar charge is plus 1 by 3. Such type of a process which takes place via Z0 exchange. Therefore, flavor changing neutral currents are not possible. Therefore, what was important point, that a charm quark was proposed by the mechanism which we call today as the Jim mechanism, and later, almost 3 or 4 years later, J by psi meson was discovered in the experiments at 2 different laboratories, and that J by psi meson was found out to be much heavier than that could be explained with the help of U, D, and S combination, U bar or D, U, D bar or US bar. Therefore, it was required that there should be a charm quark to explain J by psi meson. Later, charm baryons were observed. Then after some time in the experiments, beauty baryons and beauty mesons were observed. Therefore, this SU3 was extended to SU4, then to SU5, and finally to SU6. However, it may be noticed that Isospin SU2 is a very good symmetry as the particles falling in this multiplet differ in mass only by a few percent, which is understood as the contributions from the electromagnetic interaction is switched off. Whereas the eightfold way, SU3 is broadly broken symmetry as the mass differences are about 40%. Nevertheless, it is regarded as a fair symmetry as mass of the strange quark is almost the same as mass of the U and D quarks. The situation becomes worse when one considers charm baryons, which is almost twice massive than the mass of the lambda baryon. Therefore, charm lambda is twice massive than this lambda. This mass is 1115 MeV. This is twice of that, and still they belong to the same multiplet. Therefore, this situation was not good, and then we can summarize that in the 60s, Gell-Mann and Zwick independently proposed the quark model to explain hadron behavior. Gell-Mann called them quarks, Zwick called them S's, and experimentally they were observed in the deep inelastic scattering experiments, marking a profound shift in our understanding of subatomic particles. This is how we can understand that. On the left hand side, the result of Rutherford alpha particle scattering experiment which showed that atom has a structure, while on the right hand side, similar experiment with electron proton scattering showed that in the high Q square region, it can be seen that proton has also a structure. Thus, to summarize, we have 6 quarks today with these charges in the units of electronic charge, and the masses which I have written up 2.16 MeV, down 4.67 MeV. This is known as current quark mass, quarks in the free state. And then we have constituent quark mass also, that we will discuss in one of the classes, where what happens when the quarks are bound inside the baryon or the meson, because see, the proton has mass 938. Therefore, with 2.163 quarks, you cannot explain the mass of the baryons. We will talk about them. The mass of the top quark is 172 Jeff. And these are the various properties, quantum numbers associated with these quarks. This is known as down quantum number, up quantum number, strangeness quantum number, charm quantum number, bottom quantum number, and topness quantum number. And down quantum number for the d quark is -1, up quantum number for the up quark is +1, strangeness quantum number is -1 for the strange quark, charmness quantum number is +1 for the charm quark, and it will be -1 for anti-charm quark. And this will be discussed while talking about the d meson decay, because d meson consists of charm or anti-charm. Similarly, we have b mesons which consist of bottom or anti-bottom quarks, which has for B meson, if we have a bottom quark, the bottomness quantum number is -1, while it is +1 for the anti-bottom. The topness quantum number is +1 for the top quark and -1 for the anti-top quark. And then in our next class, we shall give a detailed description of why the isospin quantum number which was introduced to us, really we have the evidences that isotopic spin dependence is there when we discuss the different proton-proton, pion-nucleon or sigma kaon-proton scattering and the decay rates. And that will convince us that really there is an isotopic spin 3/2 dominance, and we can understand, we can predict the cross sections. If we have measured the pi plus p scattering cross section, then based on isotopic spin algebra, we can predict pi minus p elastic scattering cross section, or pi minus p going to pi 0n pi 0n scattering cross section, or pp going to pi plus d scattering cross sections. If we know, then we can predict pv plus n going to deuteron plus pion scattering cross sections, etc. Let us stop here and we shall start from this place. Thank you very much.